obvious way, you can use the separable ODE method to solve it. Yeah, so I think on your scratch paper, you can find a solution. You just put it aside. Now, we want to use a different way to solve it. Yeah, yeah. So the reason because for the learning purpose, so we want to learn a new method. Okay, yeah, all right. Yeah. So let us consider a second way. Yeah. So we use the differential form. Okay. Yeah. dy y prime dy over dx. Okay. Y prime, that is dy over dx. Yeah. So then we, remove the common denominator, so we get a differential form. Yeah, after, some simple algebraic manipulation, we get this differential form. Okay? Yeah. All right. Because last time we learned there is a method about, we use the total differential, right? Yeah. So we check the exactness of this differential form. Yeah. So let's do that. Okay? Yeah. So we want to, try to understand using a new method. Yeah. The criteria, yeah. Based on that criteria, yeah. Partial m over partial y. This is m. Okay. This is m function. Yeah. M function. M function equals 1, right? Yeah. Constant 1. Okay. Partial m over partial y, yeah, you take partial derivatives, 110. Yeah, 110. Okay, yeah. But partial n over partial x, 1, the partial derivative, that's 0. Okay? So these two numbers are different. That means this differential equation is not exact. Okay? It's not exact. Yeah. Then we cannot use our total differential method to find a solution. Yeah. Doesn't work. Yeah. But here, because there is a, based on our experience, if it does not satisfy the exact form of the differential equation, we still will have a chance if we can convert it to exact form. Then we can use the total differential method to find a solution. Yeah. So we need to do some, extended work. Yeah. Try to find a way to make it exact. Yeah. Make it exact. All right. So our next question, how to make it exact? Yeah. All right. So that's reduction to exact form by integrating factors. Yeah. Integrating factors. All right. So that method. Yeah. Some of you learned it before. Okay. Here we just review. Yeah. Yeah. All right. Consider the differential form. This time we consider the general differential form. Yeah. P of xy and Q of xy this time. Yeah. Here you can see, yeah, in our previous differential form we use m and n, right? Yeah. Because here the reason people change to P and Q, because this time the criteria is not satisfied. Okay? Yeah. For m and n, we assume the criteria is satisfied. So we use m and n when the criteria is satisfied. Yeah. But it's not a big deal. P, Q, M, N, it's not a big deal. Okay? Yeah, but here people intentionally use the different P and Q. Because after we convert it to exact form, then at that place we need to use M and N, right? So we don't want to get ourselves confused. Yeah. So this non-exact form, we use P and Q. But After we do the conversion, we will get an exact form. Then we, at that place, we use m and n. Yeah. All right. Here we assume partial p over partial y is not equal to partial q over partial x. Yeah. All right. Then, before we work on, because when we develop, we need to work on many abstract formulas. Yeah. All those formulas, when we do computation, very abstract. Okay. So in order to make you feel more comfortable, we want to work on some simple, concrete example to make you feel better. Okay? So you can see something concrete, so you'll feel better. Then after that, then we work on the abstract formula development. Yeah. All right. So this simple example, very simple. Yeah. Look at this differential form. Okay. Yeah. So simple, right? Yeah. Okay. Here you can see P. Here we use PQ. Yeah. P is negative y, and Q is x. Yeah. So simple. Yeah. Now let's check the criteria. Yeah. Partial P over partial y, -1. Okay. Yeah. Partial Q over partial x, +1. They are different. Yeah. So it's not an exact differential form. Yeah. All right. But this time we want to rescue the method. Okay? We want to rescue that total differential, that method. Yeah. How to rescue it? Right. Now we multiply a special factor. Yeah. Later we'll call it integrating factor. Yeah. Here we need to multiply a special factor. The good thing about this equation, when you look at, let's look at the structure of this equation. Yeah. Left-hand side is a differential form. Right-hand side is 0. Right? 0. Yeah. You know, 0 is a good number, right? 0. 0 has many good properties. 0. One property is 0 multiply anything is also 0, right? That property is great. 0, if you multiply 0 with any expression, it's also 0. Okay? All right. So now, let's do it. Let's multiply both sides of the equality by same expression. How about that? Yeah. In that way, you only do multiplication at the left-hand side. Right-hand side always 0, right? Yeah. But the left-hand side, you will get a different differential form, right? After you multiply a factor. Can you imagine when you multiply some appropriate factor at the left-hand side, you make it exact. You make the differential form exact. There is a possibility, right? Yeah. Now let's try that idea. We multiply an appropriate factor. Yeah. So, the criteria not satisfied, so we, put a cross there. But the new idea, let's choose important appropriate factor. That factor is 1 over x squared. Yeah. How to find it? Later we will develop. When we do our formula development, we will find that. Yeah. Here, just like magic, okay? There is 1 over x squared. It's a magic factor. All right? So let's just try it. You multiply 1 over x squared both sides of the equation, you will get this. Yeah. When you write in this way, it's look like redundant, right? Yeah. Sometimes the redundant form helps a lot. Okay. Yeah. Here it's we make the form more complicated. Yeah. After we multiply a special factor, we make it more complicated. Yeah. But this new form helps a lot. Yeah. Let's see. When we apply partial p over partial y, we get a -1 over x squared. When we calculate partial q over partial x, we also get the same negative 1 over x squared. There. So this new form becomes exact. So this time, we get an exact differential form. So we can use the total differential method to find the solution. Yeah, see? Yeah. Yeah. All right. So then, how to find the solution? I think it's easy, right? Yeah. Total differential, the u, right? So we, yeah. All right. Integrating factor. Yeah. But this simple example tells us, yeah. So we can do some special manipulation. You can see the key to the success is you need to select appropriate factor function. Appropriate factor function. Yeah. So if you can find appropriate factor function, then we can convert it to an exact ODE. So then we can use that total differential method to find the solution. Yeah. All right. So let's do it. Yeah. Yeah. So let's determine that appropriate factor f. Yeah. Here we use the unknown function. This f is an unknown function. We need to determine it. Okay? Yeah. Nobody is that smart. You can guess the right f function, right? Yeah. Nobody is that smart. Okay? Yeah. The magic, nobody can guess that. So we need to, through the rigorous calculation, we need to find that f function. Yeah. So let me explain how to calculate, how to find the f function. All right. Then we require this criteria, right? After you multiply certain f, we need this equality true. The goal is we want to find appropriate f, and the objective is we want to make this partial derivative equality true to determine that capital F function. Okay, yeah. All right. So next, let us apply the product rule of derivative. Partial derivative, yeah, we also use the rule, product rule. So by simplified notation, yeah. Product rule, the left-hand side, we have two terms. Yeah. F sub y, that's the simple short notation, simplified notation for partial derivative. Okay? Yeah. Yeah. Because when you write partial derivative, sometimes you want to use the simplest form. Yeah. So here, f sub y means partial f over partial y. Yeah. That notation. Okay. So f sub y times p plus f times p sub y equals f sub x times q plus f times q sub x, based on the product rule of the derivatives. Yeah, pretty straightforward. Yeah, but the question is, yeah, here I want to talk about problem solving. Yeah, some common situation in math problem solving. Yeah. So you may have this, yeah, so especially in your future real world applications, you may have this situation. Okay? If you encounter this situation, then learn the thinking method, how to find a solution. Yeah. All right. Here, if you examine this equation, do you feel it's complicated? Do you think it's complicated? Yeah. Let's look at term by term. Which part is known? Which part is unknown? Okay? Known and unknown. Yeah. Let's try to see it. P is known, right? Yeah, P is known. P sub y is known, right? Yeah. Q is known. Q sub y is unknown. Right? Yeah. And any function related to f is unknown. Right? Yeah. So f is unknown, f unknown, f sub y unknown, f sub x unknown. Here, you can see the unknown, too many unknown expressions, right? You have f unknown, f partial sub y unknown, f sub x unknown. It's too complicated, right? Yeah. If you do not simplify this form, too hard to solve. Too hard to solve. Okay? Yeah. So the next step is, now, can we make it simpler in this situation? Yeah. Remember, in one lecture, we learned that golden rule. Still remember golden rule? Yeah. Our textbook mentioned the golden rule. Yeah. What's that golden rule? So here, let's recall. Okay. Yeah. So probably in our, part A, right? In our part A. Yeah. Maybe the first or second. I couldn't remember. But there is a golden rule. What's that? The golden rule tells us when you solve a problem, if it is too hard, then you try to make it simpler. You try to solve a simpler version. Is that golden rule? The basic idea is like this. Okay? Yeah, here we have that situation. Yeah. Because this equation is too hard to solve. Okay? The unknown functions, too many unknown functions. Yeah. F sub x, f sub y. 3 unknown functions, expressions. Let's say 3 unknown expressions. Too hard. Then, by the golden rule, can we consider a special case of f? Yeah. Because f can be chosen in many different ways, right? We have a lot of freedom choosing x, right? F. We have a lot of freedoms to choose f function, right? Can we choose some special f function to make it simpler? Yeah. By the golden rule, you pick the simpler special case. That's the golden rule, simpler special case. Here, can we pick a simpler special case for f? Yeah. Yeah. Think about that. Simpler special case for f. We follow that thinking line, okay? Thinking direction. We follow that thinking direction. All right, yeah. All right. Yeah, so that golden rule, right? So, it's important, that golden rule, all right? All right, so let's do the simplification. Can we choose the special f that's only the function of x? It does not contain y. It's a special case, right? It's a brave assumption, right? Yeah, yeah, because we may worry it may not work, right? Yeah, this brave assumption may not work. Yeah, all right? Yeah, here you see when we write this way, f equals f of x. There is no y. If there is no y, that means if you do partial f over partial y is 0. Partial f over partial y, that term is 0, right? Yeah. Think about it. So this first term will be gone, okay? The first term will be gone. Then you simplify it, right? Yeah. Yeah. So we take that away. Yeah, by golden rule. Yeah. Golden rule tells us we can try that. At least we can try it. If it doesn't work, we try something different, right? Yeah. Yeah. So we need to do experiment. Yeah. All right. Now, after simplification, we get this new equation. Do you feel a little better on this equation? Do you feel a little better? Yeah. Because in this new equation, f is unknown, f prime is unknown, f unknown, but the unknown is f and f prime. Then we have a chance to solve, right? Yeah. It's a pretty much some ordinary ODE, right? If you treat f as y, so you have y prime, that's all you have, right? Yeah. The remaining known functions, p, q, partial known functions. So you have ordinary ODE. Okay? Yeah. So then you have a good chance to solve it. All right? Yeah. All right. So we work on this. Then we try to manipulate. Yeah. So we divide the new equality both sides by this capital F and Q. Yeah. After division, we can write F prime over F. Left-hand side, unknown terms, right? Yeah. F prime unknown, F unknown. So we put unknown terms at the left-hand side, F prime over F equals right-hand side, all known terms, right? Yeah. P, Q, known, and a partial P sub Y, Q sub X, all known. So the right-hand side is known, all right? So you get F prime over F equals a known function. How about that? How about that? Okay? Yeah. All right. So the good thing is the right-hand side is a known function. Okay? Yeah. The left-hand side to be solved, to be determined, F. Yeah. But when you look at this new form, can you see something, some potential contradiction in this new form? Potential contradiction. Potential contradiction. Yeah? Because when we make some brave assumption, we may cause some problem from our brave assumption. So there is a potential contradiction. So we need to be aware of it before we move on to solve the equation. The potential contradiction is, look at the left-hand side. Look at left side. Because based on our assumption, f is a function of x. There is no y involved in f function, right? So at the left-hand side, f prime over f, there is no y involved in the left-hand side function, right? How about right-hand side? Is there y involved in right-hand side? If there is a y involved in right-hand side, then you cannot find a solution. Yeah. Because left-hand side, no y term, but right-hand side, you have explicit y terms. How can you make them equal? No way you can make them equal, right? Yeah. That means your assumption is wrong. Your brave assumption, your initial brave assumption is wrong. Structurally wrong. You guess a wrong structure. So our brave assumption, that's our guess, right? That's our guess. But our guess is fundamentally wrong. Structurally wrong. Then we cannot solve it. Okay? So to be able to solve in this way, our requirement is the right-hand side expression does not contain any y. No y involved. So that means if we are lucky, if we are lucky, okay, to make the right-hand side expression excluding any y terms, then we can find a solution. We can find a solution. Okay? Yeah. 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 All right. So that's the limitation of this method. Okay? This method has limitation. Yeah. All right. Yeah. Yeah. So here, based on that, we let capital R, we introduce a new function R. All right. The reason we introduce new function R, because this whole expression, this whole fractional expression, too complicated, right? If we write whole expression, we need to, do a lot of work. So when we introduce a new function R, yeah, we only use one R to represent that whole complicated structure. So yeah, so that's the reason we define capital R equals this, fractional structure. Yeah. All right, and we need to assume this time that R only depends on X. Otherwise, this method fails. Otherwise, this direction fails. This direction fails, it does not mean all direction fails, right? We can explore other directions, right? Yeah. So this particular direction fails. Yeah. We need to, you know, explore different directions. Different directions. Yeah. Yeah. All right. Yeah. So if we're lucky, that means capital R function does not contain any y terms, then we can find that so-called integrating factor f function by exponential function. The exponent is integral of that r function. Yeah, because we just solved this equation, we will get that. That equation you can use the separable method to solve it. Okay? Yeah, the solution you will get exponential function e, exp, e function. Okay, e to that exponent part, it's an integral of r function. Okay, that is the integrating factor. Yeah, but here, when you do that, there are some conditions. You need to keep your eye on it, right? Yeah. If this critical step fails, then you need to drop this method, then you work on a different way. Yeah. All right. Yeah. But you have some hope. Okay? All right. So here. So let's assume if the previous direction fails, okay? If the previous direction fails, we need to change a new direction. Okay, our new direction. How about we have a chance to try f is a function of y without x involved. Yeah, some symmetric possibility, right? This is a symmetric possibility. Yeah. F could be a one variable function of x, but it's also possible that f is a one variable function of y, right? So another possibility. If the first possibility fails, we can do testing on the second possibility. Yeah, same logic. Yeah, everything the same. Yeah, but this time with respect to y. Yeah. All right. So there, we need to solve this one. Yeah, so we do the similar operations. Yeah, but this time, f sub y over f is this known function, right? Known function, can we use a r star? Yeah, so it's a different r function, different r from the previous one. So here we use r star function. That r star function should be a function only rely on y, no x, right? Yeah. Because left-hand side, it's a function only with y involved, no x terms in the left-hand side function. Yeah. All right. So only depends on y, otherwise it fails. Yeah. So here, at least we can try two possible ways. Yeah, two possible ways. Yeah. All right. So here, let me ask you one question. Yeah, so here, these two ways, we have two chances. Let's say we have two chances to extend our non-exact differential form. Two chances. Yeah. So here, there is a question. Yeah, there is a question. Yeah. Sometimes, there is a possibility. Sometimes both ways work. How about that? Both ways. So r function is only a function of x. R star function is only a function of y. Both correct. So which way to go? Which way to go? Yeah, both way you can reach your destination, but which way you want to go? In your real world experience, if you can go to one place, your destination in two different ways. Both ways you can get to your destination. Which way you want to go? Yeah, shorter or simpler, easier way, right? Here, we also take that logic. We pick the easier function, right? R function easier or R star function easier, right? You can see, yeah. Sometimes R function easier, sometimes R star function easier. For example, one function is just a constant. Another function is non-constant. Definitely you want to choose the constant function, right? Yeah. So you pick the easier way if both way works. Okay? Yeah. All right. Yeah. Yeah. So here, yeah. So you can try these two ways. Yeah. Let me ask you another question. Right, all right. For this extended method, right? Yeah. If you try both ways, these two ways, both fail. Yeah. Do you still have a chance to find an appropriate f if both assumptions, yeah, because that's our assumptions, okay? Yeah, first assumption, second assumption. If both assumption fails, do you still have chance to find an appropriate f function? Yeah. The answer is yes. Yeah. Yeah. Because those two functions, just the two special functions, right? Yeah. You may try the third special function. How about that? Is it possible you can try third special function? Yeah, that's possible. Yeah. Yeah. Actually, we have an exercise question. Yeah. In our textbook, there is an exercise question. Yeah. So we need to use one special way that's different from first way and the second way. Yeah. There is a third way. Yeah. But third way, yeah, much harder. Yeah. Because you need to do much more work. Yeah. 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 Much harder to find an appropriate third way. Yeah. All right. Yeah. Yeah. So let's continue. So let's complete the remaining slide. A summary. Yeah. Summary. So yeah, you can try those two simple ways. Those two relatively simple, right? Yeah. So before you try some harder way, yeah, let's try these two simple ways first. Relatively, I want to say relatively simple. Yeah. All right. So you calculate these two expressions and check, if the first expression is a variable x, so you have a candidate, okay? The second expression is a variable y, you have another candidate. Yeah. So if both you have two candidates, then you need to select the easier one. Okay? Yeah? All right. Yeah. Both work, then take the easier one. Yeah. So then, after that, because after you select, you find the f, now you can solve an exact form. You will get an exact differential form. Then you just use our total differential method. You can find a solution. Yeah. Okay. Yeah. So here I do not need to, I think it's enough for us, right? Yeah. Yeah. Enough for us. All right. Yeah. So the last thing now, let's look at one simple example. So this example, yeah. First, we want to write a p function and a q function. Yeah. Then we calculate the partial derivatives and compare if the exactness criterion is satisfied. Okay, exactness criterion is satisfied. Yeah. All right. Yeah. Actually, here we directly calculate the r and r star. Yeah. Because if the exactness criteria is satisfied, then R and R star both 0, right? Yeah. Or one of the two is 0. Yeah. All right. Yeah. But here it's not 0. Here R, when we calculate this R function, it contains both x and y. That means we cannot use it as a candidate, right? It cannot be used as a candidate. Yeah. All right. So then let's calculate R star. R star -1. Yeah. So then it's a valid candidate. Right? Yeah. So we can calculate the integral. Yeah. All right. Yeah. So f of y is equals exponential function, yeah, of integral R star, but yeah, R star negative, that's easy. -1, right? The integral is -y. So e to the -y. Yeah. Here you can ignore the constant, yeah, because that indefinite integral, usually you may want to include a constant, unknown constant, right? Yeah. But here, because we only need to determine one integrating factor, when we need to choose constant, we want to choose the simplest constant, right? So we want to make our life easier, so we always choose the simplest. So let's just drop that constant. Yeah, because we only need one function, right? Yeah, we do not need all such functions, right? We just need one of the bunch of functions, only one. Okay, yeah, we just choose the simplest. Here we choose e to the -y, as simple as possible. Yeah, then we multiply this integrating factor both sides to make it exact. This time, yeah, if you want to check exactness, check for the exactness. Yeah, it's okay. Yeah, but we expect it must be exact, right? Yeah, we expect that. All right, so you can check it. Yeah, then it's correct. Yeah, but sometimes if you check, it may not be correct, right? Because your computation could be wrong. You need to double check your computation. Yeah, you may miss something here and there, right? Yeah. You need to carefully go through all the steps of your calculation and fix all the problems. Yeah. Yeah. But your goal, you want to see these two expressions are the same. Yeah. So then you can, use our usual way to solve it. Okay? Yeah. All right. So remember, yeah. Remember the last lecture, I redo it, right? When I redo, yeah, I recommend some students, if you didn't watch, I recommend you view the last 10 minutes of that video, because I add something. Okay, I add something I didn't talk in class. Yeah, so if you didn't watch the second video, last 10 minutes of the second video. So in that 10 minutes, last 10 minutes, I said, you have a shortcut way to find u. Okay, so here u equals the first expression and u equals second expression. Here there is a shortcut to find the final u. Okay, so I describe the shortcut way. The shortcut is when you write a u function, you collect the terms that appear in these two functions. Okay, all right. Yeah. So e to the x appears, so you need to include this term. Xy appear. Yeah, xy appear. You only include once. Okay, e to the negative, this include. So you need to write these three terms in your u function. Yeah. The remaining part, that's constant c. Yeah. So that's the shortcut way. Okay, all right. So here we can use the shortcut way. Those three terms, yeah, because we can use our eyes to see those three terms. If a term appears in any of the two expressions, you select it. Yeah. But do not duplicate it. Okay? If there is a term appears in both, you only select once. Only select once. Okay? Do not repeat it. So you get the right hand side just the constant C. So that's the final solution. Yeah. So that's what I said, a shortcut. Okay? Because in that way you don't need to take two more integrals. If you do not use the shortcut way, you need to, in order to determine K function, L function, you need to take two integrals. Yeah. Although not too hard, yeah, but just a little more work. Yeah. All right. So after this example, the remaining a few minutes, I think we can complete our electric circuit question. Right? We have that electric circuit question. So we complete it. So then we complete the whole part C. Yeah. Next time part D. So, to finish module 1. Yeah. All right. Yeah. Initial condition. Yeah. C. All right. Yeah. The final solution. Okay. Yeah. Because here initial condition is given, so you plug in the initial condition. Yeah. To determine that constant C. Yeah. All right. Then the last step. Now we are ready. We can use the, extended exact ODE method. We just plug in, right? This time, development is done. We just apply the formula. Yeah. All right. Yeah. But there is an initial condition. Yeah. All right. This method. Yeah. Now, because we already checked it, it's not exact. Yeah. So we need to find an integrating factor, right? Appropriate integrating factor. There are two chances we can try. Okay? Two chances we can try. The first one, we calculate R. Yeah, the first chance. What's that R? Yeah, 110. Yeah, satisfy the condition, right? Yeah. But yeah, it's already good, but actually we do not need to try the second one. But here, I just do the second one. Okay, the second one, it is satisfy the condition, but more complicated than the first one, right? Yeah, more complicated. So we should use the R function, not R star function. Yeah, R star, you need to do more computation work, right? Yeah, so we want to avoid it. We take the easier way. Yeah, all right. Yeah, so then we use R function. We can calculate the F. So that is e to the 110x. Yeah, we only need one factor, so we only take one. Okay, yeah, no C. Yeah, don't worry about C. Yeah, all right. Now let's update. We multiply this integrating factor, on the previous differential form. Yeah, so this time we expect it's an exact differential form. Okay, although you can check, if you want, you can check. Yeah, but now we solve it using the standard way to find that total differential. Yeah. All right, so integral. Yeah, on m function. Yeah, so we get this expression, and with unknown k function. Okay, unknown k function. Then the second one, the integral on m function. Yeah, this time we have an unknown L function. Then, as I said, the shortcut way, right? When we write the final U function, let's take the shortcut way. Yeah, because this term is common terms, right? The common terms we only take one copy. Yeah. So this term, it appears in the first question. Let's just copy it. Okay. Yeah. Carry over, right? Carry it. Yeah. All right. Yeah. The remaining we'll put all in constant. Okay. Yeah. Then we can write a U function in this form. Yeah. But we need to determine that constant C. So we use the initial condition. We plug in initial condition, y0 equals 0. Yeah. To determine that little c constant. Yeah. So let's plug in. Yeah. So we can get C equals negative 48 over 11. Okay, yeah, so you can do calculation easily. Yeah, so here that, yeah, because plugging 0, you can see, you know, this E term is 1, right? This E term is 1. Yeah, Y equals 0, yeah, so this term is gone, right? Then you see, you know, you can easily see negative 48 over 11. Yeah. Then, our final equation, you can write y equals 48 over 11 times parenthesis 1 minus e to the negative 110x. Yeah. You can compare with the solution you use the separable method to solve. Yeah. It should be the same. Okay? Yeah, but here we use a different way. Yeah. Although for this question it's not necessary. Okay? For this question it's not necessary. But for other questions, then you may really need that extended exact method. You have a question? Tavion? Okay. Yeah, good. Yeah. Right? Yeah. So try to understand the logic. Yeah. So why we do all these steps? Yeah. Try to understand the story behind it, development. Yeah. Many students, they just apply the formula. Yeah, it's okay. After you understand, then you just work on the formulas. Yeah. But to get a better understanding, you understand how to develop the formulas. The logic. When we develop, what's the consideration, right? Yeah. Yeah. Why we do that? Yeah. So then, because if you have that understanding, you can use that method to solve new problems, right? For example, that golden rule. I mentioned that golden rule. You can use the golden rule to solve the problems on the similar situation, right? Yeah, yeah, that golden rule. Yeah, yeah. Effective. Yeah. All right, that's it.